Good afternoon. Can everyone hear me all right? So this app has a chat if you want to ask questions. And we are recording the meeting today for the people who couldn't be here. Great, thanks, Jaylee. We'll get started in a couple more minutes. All right, everyone, welcome to Statistics. So we're meeting online today. I gather that Noonan got quite a lot of snow. So I have an in-class activity planned for section 1.2. So we're going to save that until Monday. I've moved back the homework accordingly. Today, let's go over section 1.3. It doesn't matter which order we do them, so since I have an activity plan for 1.2, we'll save that for Monday. All right, which means today we're going to understand some measurements that we take for our data sets. These are summary measurements. So I'm going to share my screen here. I have another tab open where I can see the chat. So if you have any questions, please just type those in the chat, or you can unmute yourself and stop me if you like. Oh, right, and I'm recording this meeting. Just so you know, we are recording this so that the people who aren't here can join, or can watch it later. Now, to share my screen, press this button. Okay. All right, so we'll use this as a whiteboard. So what we're doing today is measures of center and variation. Let's make the center blue and the variation can be red. So typically, I'm going to have some kind of data set. Let's just go with a simple one like height. We like to use capital letters for our variables, typically capital X and capital Y. Sometimes other capital letters like S for salary. So we could use H for height, but X is a typical choice. So if I'm trying to plot my data set here, I can make an illustration where the x-axis is height and then the y-axis is going to be frequency. And I could say something like the average person in this study was 5'7", and then the set might look something like this. Okay, so the high frequency in the middle here means that lots of people were somewhere between, let's say, 5'4" and 5'10". Those were very common measurements. And then the height of the line goes down to say that people taller than 5'10" or shorter than 5'4" are less frequent. So when I'm looking at this data set, if I'd like to summarize it, there's a couple of important things that I need to be able to describe. So one of those is center. What is the middle of the data set? And there's 3 different ways to measure that middle. We'll talk about those soon. Hold on a moment. There. Should be easier for me to write and easier for you to hear me now. So let's say that the center is here, depending on how we measure center. I could be looking at the average, or I could be looking at the middle of the list. What's the middle person, the typical person? So there's a few different ways to measure center. And then I also want to measure variation. So how spread out is the data set? Now, this curve I've drawn here is not normal. Specifically, you can see we've got 2 bumps here. A normal curve will look a little different. A normal curve is a nice perfect bell like this. But height doesn't do that for humans. If you have a normal curve and you know the center and you know the spread, then you know everything there is to know about the curve. If it's perfectly normal, there's only one curve for each given center and spread. If the data is not perfectly normal, then there will be more. But what that means, since a lot of our data is going to be normal, if we can come up with ways to describe the center and variation, then we understand quite a lot about the data set and we can use it to start making predictions. Okay. Now, before we get to these formulas, I have to show you a little bit of notation. This is the Greek letter sigma. It's a capital sigma, and capital sigma here means sum. So if I wrote add up the numbers I, where I starts at 1 and it goes up to 5. That's a way I could use the sigma notation. And again, remember, just ask in chat if you need me to slow down or re-explain something. It's difficult when I can't see your faces to know if people are taking it in. Okay, so this says, from when I is 1 up to when I is 5, sigma, add up all the values of I. So my answer would be 1 plus 2 plus 3 plus 4 plus 5. Capital sigma says add each of them. So this one would be worth 15. Or if I did n equals 2 to n equals 6 of n squared, then I would do 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. Hopefully that's making sense. And again, just stop me if it's not. I'm not going to bother finishing that computation. I just wanted to show you that's how sigma looks. So if you have your data is capital X, so that's the variable for the whole data set. And we could use lowercase x for individuals. And so if we wrote sigma little x, that would mean add all the values of x. Okay. A moment. All right. So, as long as that notation makes sense, then we are ready to look at 3 measures of center and 2 measures of variation. We'll need this sigma notation. And so, the most important measure of center is called the mean. It's also known as the average. And the way you get the mean is by adding up all the values of x and then dividing them equally. And so the formula for the mean, there's 2 different symbols, right? For a sample, the mean is called x bar, and it's the sum of all the values of x divided by n. And that's where n is the size of the sample. So if I measured 20 turtles, I would add up the lengths of all the turtles and then divide by 20. We use different letters. As statisticians, you're going to be learning about a sample, measuring the sample, generating summary information, and then using that to make predictions about a population. So the parameter for the population has a different symbol than the statistic for the sample. And here it's a lowercase Greek letter mu. And so the formula for mu for a population is the sum of all of the individuals in the population divided by capital N. And that's where capital N is the size of the population. If you only learn one of those, this is the one that we're going to use much more often. We don't actually have access to all the data values in the population, so the equation down below is more just defining it formally. It's not something we're going to use. But the one I circled in blue here we'll use all the time. So for example, maybe I stop 5 people in the hall and I say, how much money do you have in your wallet? And someone has $1, $3, $6, $10, $15. So there's my data set. We performed observations of how much cash is in each person's wallet. We got our data set. And so if I want to know the mean for this data set, well, first off, N is 5 because I measured 5 people, or 5 elements more generally. We took observations for 5 elements. And so X bar here would be the sum of all my X values divided by N. That's 1 plus 3 plus 6 plus 10 plus 15 divided by 5. Okay. So that should be 35 divided by 5 is 7. In other words, the 5 of us have $35 in our pockets collectively, and so if we pooled all the money and then distributed it evenly, each person would have $7. And that's what the mean represents. Pause for a second. Do you have any questions here? In a little bit, I'll show you how to calculate these in Excel, because some of the homework problems are pretty lengthy and you wouldn't want to do it with paper and a calculator. But first, let's get through the other 2 measures of center now. There's 2 more. The median is the middle of the list. One moment. So if you put the list in order, the median is the element in the middle of the list. There's a formula we can use. Which place? The formula is n plus 1 over 2. So here's how that works. If my X set is 1, 3, 6, 10, 15, then this 1 is in first place, and the 15 is in 5th place. Or you could switch those depending on how you order it. It doesn't matter if you order them greatest to least or least to greatest. We've got someone in 5th place and someone in first place. If I take the average of those place values, the average of 1 and 5 is n plus 1 over 2. So this is the average of 1 and 5 is 3. So if the average of first place and 5th place is 3, then the middle of the list is the person in 3rd place. And so the median is 6 for this data set. So we got a slightly different answer. That's because this is just 2 different methods for calculating mean and median. Okay. One more. This one's a not so exciting measure. It doesn't capture as much information as the other 2. The mode is the most popular value. So if my data set Y, let's say I asked everyone, how many cats do you have at home? And they said this. I asked 6 people, 3 people had no cats, and so in this data set, the mode is 0. That was the most popular answer. Most people had no cats at home. Or not the majority, but a plurality. Even if I put a 3 at the end of the vector. So now less than half the people have a 0, but it's still the plurality. More people said 0 than said any other value. So in the set X up here, actually there is no mode. In X, where every person had a different amount of money in their pocket, we say no mode. So the mode's not a very useful measure. We mostly care about the mean and the median. Okay. So now you've seen how to compute the measures of center. I want to tell you why we have, so the mode's not very exciting. We're not going to use the mode too often because it doesn't capture a lot of information about the set, just what's most popular. But we're going to use mean and median quite a bit because they do have different meanings. Okay, the mean is sensitive toward outliers. Oops, sorry. Back to drawing. So X here, what if I change one person's wealth now the 5th person, instead of $15, they have $115. So when you've got one person who is much wealthier than the rest, then the mean would be the sum of the x values divided by n. So 1 plus 3 plus 6 plus 10 plus 115 over 5. That's 135 divided by 5 is 27. Only one person got richer, but now their mean is $27. If we all split it equally, we would all have $27. So we've got what we call an outlier here. Outlier means it's beyond the bounds of the rest of the data set. It's not a typical value for this variable. And so because we have an outlier, this mean is now sitting above the other 4 of us and below the one outlier. So the mean is very sensitive to outliers. That's why, whereas the median hasn't changed, right? The median is insensitive to outliers. The median is in fact still equal to 6. So if you have outliers in your data set, that's when the median can become more useful than the mean. But if you don't have outliers, we like the mean better because the median is only looking at one person's value. The mean, in its formula, it considers every single value in your data set. So typically, we're going to use the mean in this class, but now you can see the use of the median. So for example, if my x-axis is income in the US and my y-axis is frequency, okay, on the left here, here's an income of $0, and that should actually be a lot more frequent than I drew it. Plenty of people are unemployed or working volunteer positions, working for free, working for very little. If we look at this data set, I'm going to Google real quick and find the current values. In a data set like this, the median is going to be pretty close to the mode. So the mode is the top here, right? This is the mode. The mode is whatever income was most popular. I think maybe the mode is actually 0. The median is a little bit above the mode. When I draw the median, I'm saying this shaded area contains half of the country, and this shaded area contains the other half of the country. So the median is drawn wherever those two areas are equal. So half of us make above the median and half of us make below the median. Now, I've found on Google the mean. I'm looking for the median. Here we go. Perfect. All right. So for a household, so the whole house, not just one earner, but for the whole house, in 2019, the median was $80,000. So half of all households made less than 80,000 and half of all households made more than 80,000. However, the mean is, in 2019, the mean was $170,000. Meaning if you took the income of all the households and distributed it to each of us equally, then each house would be able to take home $170,000. So only half of us are making more than 80,000, but the average of our incomes is 170. Data that looks like this is called skewed to the right. It has no left tail, but it has a long tail on one side only. We call that shape skewed right, and whenever your data is skewed right, the mean will typically be more than the median. Okay, hopefully that makes sense. Again, just let me know in chat if anything is confusing. I could give you an example that's the other way around. If I'm grading a class on test scores, here's 100%. If I don't give extra credit, no one can get more than 100%. So the class average is usually around 80, and it's very rare for people to do less than a 60. Typically, most of the class passes the test. So in this case, it looks like I'd better use the same colors, no? In this case, it looks like the mode is around 85, and the median should be close as well. The median and mode are both around 85, but the mean is significantly lower. That's because there's a tail out here. This set is skewed left. If the mode is 85 here, if you got a 100, then you are 15 points above the average. But if you got a, let's say a 25, then you are 60 points below the average. So someone who got a 25 can move the average 4 times further than someone who got a 100. If you do very well on the test, you only move the average so far. But if you do very, very poorly, you can move the average pretty significantly. So that's why when I'm curving the test, I prefer to look at the median rather than the mean as I make the curve. So when data is skewed left, the mean is below the median. Okay, so that's why we sometimes use median. And there's other more fancy measures that we'll get to later, talking about quartiles. So instead of what's the middle person have, what does the person at the 25th percentile have? We'll get to that in a little bit. But for now, that's the difference between mean and median. Any questions here? Okay, so that's our measures of center. Thank you, Shaylee. All right. Now, let me stop sharing the whiteboard for a minute, and I want to show you how to do some of these measurements in Excel. Okay, so now over here, I should be able to share content. Okay, You should be able to see my Excel screen. Actually, let me try that again. Sorry. Now you should be able to see the entire screen. That way, if I drag something over here. Okay, so I start with a simple homework assignment. I need to take the average, let's say this problem. So for the first problem, I can see that the mean is 14.5. There's two 14s and two 15s, so the average is 14.5. We can do that with a calculator or even just by looking. But this second problem here, this looks like a little bit of a chore. That's a lot of numbers. I don't really want to do the mean by hand. I would sit there, I would have to count them. So I'm counting 15 data values. That means I should add these all up and divide by 15. So what I'm going to do is copy them, go into Excel and paste. And this time it pasted without any trouble, but we can mess around with this menu if we want to try to paste it differently. There's even an import wizard if you have to. And I'm going to get these arranged in, whoops. I'm going to get these arranged in one tall line. So I'm going to cut and paste here. So now here's my data set. And in Excel, I can do this a long way where I say, let's add these all up and then divide. So first, let's add them all up with the sum command. I'm going to open a parenthesis and then select my whole data set here. Now I'm adding those up. They apparently add up to 738. I also want to know how many data points there are. And if I don't feel like counting or like looking at the row lines, I can use the Excel command. Let me zoom this in so you can see it a little better. I can use count to count a number of values. So if I just select this whole region of the screen, it's going to say there are 15 values filled in there. So this is my sum of x. You don't see anything, Kimberly? Can anyone else see that, or am I the only one who can see it? Shaylee can see it. Some people can see and some people can't. That's unfortunate. But you were all able to see it when I was sharing on the iPad? What is the? Oh, I see. For some reason, only the verified users are able to see this. I don't know why that would be. Let me see. I wonder if there's a, oh dear. You can see it? Oh dear. I'm sorry. I don't know the technicalities of these things. Is it possible it's just in another window? Tell you what, I will. How can I fix this? It is being recorded, so worst case scenario, you should be able to go back and see it if you watch the recording. Otherwise, I guess you could try leaving the call and rejoining. I don't know if that will work. Sorry, folks. Well, I'll keep going with this in a minute then. Okay. So I've got the sum of all my data points. I used the count command to count all my data points. And then I can just say my average is equal to this number divided by that number. And so the average of all these points should be 49.2. And if I put that over here, I should be correct. Okay, so my Open Math liked that. By the way, we're going to want to do one more decimal place in the answer than was given in the problem. Since the problem had no decimal points, I gave an answer with 1 decimal point. That's called the round-off rule. You never want to round in the middle of the computation. You just want to round your final answer and give 1 extra decimal point. Okay. One other thing I can do in Excel, if I want to do this a quick way, is say average. The average command, and by the way, this will also work in Google Sheets. The average command, if I highlight all of these, gets me that same number in 1 step. Okay, so if we just have a data set, then that's what we're going to do. But sometimes they give us more than just a data set, and so I want to show you what to do in those situations. So here's something more complicated. I want to know how many cats people have. And so let's say I make a data table. How many cats does this person have? Let's keep it simple, 0, 1, 2, or 3. And what are the frequencies? So 15 people have no cats, 5 people have 1 cat, 10 people have 2 cats, and let's say that 10 people have 3 cats. So here's my data set. I would like to take the mean. In other words, if we distributed the cats equally, how many cats would be in each home? And that'll be a decimal with 1 decimal point, because the data has no decimal points. Okay, so in this case, whoops, that's not what I wanted. Share screen. Okay, so we should be back on the iPad. All right, so for a frequency table, we're going to say X is the data value and F is the frequency. So in this case, I said that there would be 15, 5, 10, and 10. So I would say 10 is the frequency for the X value 3. Then one way to get the average, first I need to add up the frequencies. So n is 15 plus 5 plus 10 plus 10, that's 40. There are 40 people in my survey who said, we may or may not have cats at home, but we'll answer your question. So I could do 0 plus 0 plus 0, a whole bunch of zeros, 15 zeros, and then 5 ones, and then a bunch of 2s, and then a bunch of 3s, and divide that all by 40. But that's not very efficient. And so what I'm thinking is, if I have 5 ones, that's the same as 5 times 1 in the sum. Adding together 15 zeros is 15 times 0. Adding together 10 2s is 10 times 2. Okay? And so the formula I'm going to use is that the mean is the sum of each x value times its frequency divided by n. And here n was the sum of all frequencies. Okay, so in this case, I could say that there were 15 people with no cats. There were 5 people with 1 cat, 10 with 2, and 10 with 3. If we add those all together and divide by 40, what does that tell us? 5 times 1 plus 10 times 2 plus 10 times 3. These people have a total of 55 cats in 40 houses. If we divide 55 by 40, we get, well, the calculator would tell you that that's 1.375. But we want to round to 1 more decimal place than the data had, and the data didn't have decimals. So we will write this as 1.4. We'll round up and say that's our mean. So if we took 55 cats and distributed them evenly to 40 homes, each house would have 1.4 cats. That's what we do with a frequency table. All right, does that make sense? I guess I can't see you nodding. Hopefully that's making sense. Again, stop me in the chat if anything's not. Okay, so that's what you do with a frequency table. But one more thing that could happen is that we get continuous data. Number of cats is discrete data, right? But how long can you hold your breath is continuous data. How many seconds? 8.4, 10.32? So if we have continuous data, well, we can still do something here. So let's say, what could I ask? How many pounds of rice are there in your kitchen? And then F for frequency. So 0 to 3, 3 to 6, 6 to 9, 9 to 12. How many pounds of rice do these people have in their kitchen? And we get numbers something like this. I'd like to find a mean. I don't know exactly how many pounds of rice each person had, so I can't add those, but I can get a good estimate. I can get what's called a class midpoint. This is X with a hat. X hat is called the class midpoint. And so X hat for 0 to 3, on average, these people have 1.5 pounds. Between 3 and 6, the average is 4.5. So these 13 people, I don't know how much rice they each had individually, but I'm going to add 4.5 pounds for each of those 13 people, because 4.5 is the middle of that class. So between 6 and 9 is 7.5. Between 9 and 12 is 10.5. So each of those 8 people with 9 to 12 pounds of rice, they're going to count for 10.5 in our approximate mean. And then our formula is sum f x bar, oops, not bar, x bar is the mean. I want the sum of f x hat, which is the class midpoint, divided by n. So the first thing I can do is find out n is 5 plus 13 plus 12 plus 8. That's 38 people. And then the next thing I can do is multiply my f's times my x's. And if you're working in Excel, which I'm not going to do because not everyone can see it, you would want to make a new column for f times x hat and add these together. So 5 times 1.5 is 7.5 pounds of rice. If 5 people have roughly 1.5 pounds each, together they have 7.5. And so 13 times 4.5, can't do that in my head, turns out to be 58.5. 12 times 7.5 turns out to be 90. I could have done that. And 8 times 10.5 is 84. I can do that. Okay, so we know for each class of people how many pounds of rice are in that class now. And so we're going to add together 7.5, 58.5, 90, and 84. We'll add together those numbers. That's all the rice in all the kitchens of all 38 people, so we'll divide it by 38 to get our answer. What would that be? 7.5 plus 58.5 plus 90 plus 84. So there are 240 pounds of rice by our approximation. And so 240 divided by 38. The computer says 6.3158. But our data didn't have any decimal points, so we'll report the mean as 1 decimal point. On average, there were 6.3 pounds of rice in each kitchen. Okay, and so that's how we get a mean if we have this generalized frequency distribution table. Again, the table I drew here is called a GFDT, and you'll work with those in your 1.2 homework. But don't worry about that just yet, because we're going to cover that topic on Monday when we're back together. All right, so that's measures of center. There is one more thing I need to teach you to do here. It's not exactly a measure of center, but it goes with the measures of center. Let's show you how to take a weighted mean. This could be useful, for example, if you were doing stratified sample. Do you remember how the stratified sample works? If I had 200 students, most of them have cats, dogs, or nothing. If I want to get information on lizard owners, I have to actually get some lizard owners in the study. So a weighted mean could look like, what are your annual vet bills? And then what percent of the population have this pet? Excuse me. So we got a bunch of pet owners together. And some had a cat, and some had a dog, and some had a rat, and some had an isopod. Well, probably more than one isopod. And you shouldn't keep rats alone either. You know isopods, right? They're the little pill bug friends. They're popular as pets, it turns out. So, let's say 40% of the population had cats, and another 40% had dogs, 15% had rats, and 5% had isopods. And then the vet bills look like the cat per year is going to spend about $300. Per year, the dog is spending $500. Per year, the rat people are spending $150, and the isopod people generally don't see veterinarians. There's not much a vet can do for a bug. So these are the vet bills. But now I took a stratified sample, which means I got 40 cat owners, 40 dog owners, 40 rat owners, and 40 isopod breeders. I can't just take 300 times 40 plus 500 times 40, because out in the real world, cats and dogs are a lot more popular than rats and isopods. So what I'm going to do is the same formula, basically. Multiply x by the weight, and then divide by the sum of the weights. In this case, these four numbers add up to 100%. So I got a whole population of people with pets. What we're going to do is say there's a 40% chance that you have $300 in bills. There's a 40% chance that you have $500 in bills. There's a 15% chance that you have $150 in bills, and so on. The last one would be 5% of 0. I don't have room. And we'll divide that by 100%. So 40% of 300 is 120. 40% of 500 is, I should know that, 200. And 15% of 150, I think I know it, but I'm going to use a calculator just in case. Okay, I was right. So we add those together, and we get $342.50. So the average pet owner's bill is $342.50. It's a little bit high because the dog owners are spending a lot. The isopod owners aren't spending anything, but there's not very many of them to bring the average down. Okay, so that's a weighted average. Is that making sense? Another thing I could do is, if I want to know my GPA, and so I have math, English, science, and art. Math is 3 credits, English is 3 credits, science is 4 credits, art is 2 credits. And my grades. Let's say I get an A in math, B in English, C in science, and D in art. Now A is worth 4 points, B is worth 3 points, C is worth 2 points, and D is worth 1 point. I cannot just take the average of 4, 3, 2, and 1 and say my GPA is 2.5. That's not going to be accurate because art is worth less credits and science is worth more credits. So when I get my GPA, the way I actually calculate it, again, is with a weighted average. The grade is our X and the credits are our W. So we're going to do multiply W times X. I have 3 credits worth of 4.0. I have 3 credits worth of 3.0. That's 9. 4 credits of 2.0, and 2 credits of 1.0. So all of my quality points, W times X, those are going to add up to 12 plus 17 plus 2 is 31. I have 31 points in this column. And then what I do with those is I have 12 credits, so I do 31 divided by 12, and that's my actual GPA. So if we just took a straight average, it would have been 2.5, but in this case, our GPA is 2.58, and that's because science was worth a little more and art was worth a little less. So our GPA went up by a little bit because art was only 2 credits. Okay, and that's a weighted average. All right. So now we're definitely done with all the measures of center. You won't need to do a weighted average unless you are doing a stratified set later. So we don't need to worry about that right now. There'll be 1 or 2 in your homework just to get us used to them. What we want to do for the rest of the class is, let me tell you a physics thing, and then we'll talk about measures of spread. I'll hold off on the physics thing. So measures of spread. Min is the lowest value, and max is the highest. And so the range is max minus min. Range is a very simple measure of spread. If my data set looks like 3, 4, 5, 7, 10, then the range, well, the max is 10, the min is 3, and so the range 10 minus 3 is 7. And that's all I'm going to say about range. You can see it's not a very exciting measure. Like the mode, it doesn't capture a lot of information. We want a measure of variation. How much is the set spread out? And range does that. But we want one that works like mean. We want a measure of variation that includes every single point in the data set. So what statisticians came up with is not simple, but I'll show it to you. And this is going to be one of our most important things in the class for the rest of the semester. So unfortunately, we're going to have to get used to this not very simple. All right, let me start with a really simple data set. Let's say capital A. Let's say my data set contains 1, 2, 4, and 5. Then x bar is 1 plus 2 plus 4 plus 5 divided by, silly me, divided by 4 because n is 4. There are 4 people in the set. So that's 12 over 4 is 3. X bar is 3. Here's what this represents physically. If I draw a number line, here's a person at 1 that has a weight of 1. Here's a 2, here's a 4, and here's a 5. Imagine that that was a physical object. In class, I would be pantomiming right now. Here's a physical object, and you want to balance it on your finger. Then the balance point is the mean. If we put the fulcrum right here, then this thing should balance perfectly at the point 3. So the 2 is a little bit closer, the 1 is a little bit further away, but the total lever force that the 1 and the 2 are pushing, so these are pushing down like a lever, these are pushing down like levers. The levers are all perfectly balanced. So if you set this on your finger, you can spin it like a basketball with your finger at 3 on the number line. Okay. And then you can see how the mean is sensitive to outliers. If my data set B is 1, 1, 1, 9, there's my outlier. Then here's my number line, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have 3 weights on the 1 and 1 weight on the 9. So where do we think that's going to balance on our fingers? We can do our computation. It turns out that X bar for B is also 3. So once again, if we put the fulcrum here, we can balance it on this point. And that's because of the physics of levers. If you're pushing down on a short lever, here this lever has a length of 2, then you don't get a lot of mechanical advantage. But if you're pushing down on a lever of length 6, you get quite a bit of mechanical advantage. So even though the points at 1 weigh 3 pounds and the points at 9 weigh 1 pound, 9 has a lever that's 3 times longer, and so the system is balanced. So there's your physics for the day. If you don't like the physics explanation, don't worry too much about it. But there's your physics explanation. So the fulcrum on which the set is balanced based on the principles of lever forces. I know just enough physics to tell you that. I only took 1 physics class in high school, never took it in college, so I'm relying on a very simple understanding here. But this is what they were thinking of when they came up with the mean. They were thinking, where does the set balance? Okay, but these 2 sets have something else. The set A is not very spread out. The set B is a little bit more spread out. We want to try to quantify how spread out these sets are. And sure, in this case, range would work. A has a range of 4, 5 minus 1 is 4, and B has a range of 8, 9 minus 1 is 8. So in this case, I could differentiate between these sets with range. So here's a pair of sets that I couldn't do with range. All right, here's the middle. And in the first set, there's 1 outlier on each end, and then everybody else is hanging out right at the middle. And in the second set, here we are again. There's 1 outlier at each end, and then the rest of the set is hanging out with the outlier. Okay, let's call these C and D. So the mean is the same, and the range is the same. So range is not good enough. I need another way to tell these sets apart, because you can see, intuitively, D is more spread out than C. Okay, here's where it gets a little bit fantastic. Picture a figure skater on ice. Okay, do you have that image in your mind? Someone is skating on the ice rink, she's doing a dance, and when she spreads her arms out wide, so D has its arms spread out wide, then she spins slowly. But when she tucks her arms into the center, then she can spin much more quickly. So if you've seen a figure skater do this, they will hold their arms out and start a spin. I'm pantomiming even though you can't see me. They'll hold their arms out and start spinning, and then they'll tuck all their limbs close to their torso, and their rotation will speed up dramatically because energy is conserved, so the velocity has to increase because what's known as the moment of inertia has gotten smaller. If you were trying to spin sets C and D on your finger like a basketball, or like a pizza, say you're spinning a pizza on your finger, D with all the weight on the edge is going to take more effort to spin. It has more inertia. C has less inertia because most of the stuff is near the center. And when you're spinning something that's close to the center, it's not going very far, so it doesn't take much of a push to get it going. Okay, the early statisticians were physicists, and this was the metaphor they used to construct a measure of spread. So that's the physics of it. D will have a larger spread than C because it's harder to get D spinning, it's easier to get C spinning. You see the lengths of those green arrows, the points in D have to travel a lot further. So getting it spun up to the same speed will be a system with a lot more energy than C has. The moment of inertia is going to tell us if all the mass was right here and right here, that's how hard it is to spin this thing. And C is going to have a much shorter one. That's how hard it is to spin this thing. It's like all the mass was at those green ticks. And so the distance from X to the green tick is what's called S, the standard deviation. Goodness, that's complicated. The good news is you don't have to design a spinning physical object. You're not going to have to work with the physics of it. As long as you can work with formulas for S, you don't have to understand the physical explanation. The bad news is that the formula is a little bit rough as well. So here we go. S is given by, it's many steps. So first off, I need to know X bar. And then I do X minus X bar. Then I square that and add them all together. I divide by n minus 1, and then I take the square root of that entire thing. We'll talk about y in a minute. WHY. We'll talk about the reason for doing this in a minute. But there's your formula. That's for a sample. And you shouldn't ever need it, but if you want to do for a population, it's muted a little differently. First off, the symbol is a lowercase Greek sigma. That's a sigma. It's the sum of x minus mu squared, because mu is the population mean. And then it's divided by capital N, and there's no minus 1. So what is this minus 1 doing here? It's a long story. The minus 1 is named Bessel's correction, in case you see that. This minus 1 is named Bessel's correction. And I think for now, let's just try to use this. Let's not try to explain why Bessel corrected it. We'll talk about meaning in a little bit, but for the next part, I want to show you some computations. Let's take this formula apart. First, find x bar. 2, find deviations, x minus x bar. So that would be asking, how far am I from the middle? Here, we can set up a table. Our set A was 1, 2, 4, and 5. And x bar for A was 3. So step 1, find x bar. Step 2, let's look at our x values. My x's are 1, 2, 4, and 5. So in the next step, deviations, x minus x bar. I'm going in PEMDAS order, right? That's inside parentheses, so it goes next. Looking at the circled formula for S, x minus x bar is in parentheses, so it goes next. This is called the deviation. How far is your point from the mean? 1 minus 3 is negative 2. 2 minus 3 is negative 1. 4 minus 3 is 1, and 5 minus 3 is 2. So the point 5 is 2 to the right of the mean. The point 1 is 2 to the left of the mean. It's a quantity with a plus or minus sign that tells you whether you're to the right or to the left. So that's called your deviation. It would be very simple if we could just take the average of all the deviations, but if you think about it, that average is going to be 0. On average, we are neither left nor right of the average because the average is the average. So it wouldn't be the average if we weren't balanced around it. So we do something complicated. Following PEMDAS, following the order of operations in the circled formula, the next step is to square the deviations. We're going to do the x minus x bar. Exponents come after parentheses, so we square. So negative 2 squared is 4. Negative 1 squared is 1, 1, and 4. These are the square deviations. So if the original was in inches, I have 4 turtles, and they're 1 inch, 2 inch, 4 inches, and 5 inches. The 1 inch turtle is 2 inches shorter than the average, but its square deviation is 4 square inches. Okay. Still looking at that formula circled for S. Step 4 is to add. I'm going to add up all of these x minus x bar squares. So here, I add these all up and I get 10. All my turtles together have 10 square inches of deviation squared. 5 divide by n minus 1. All right. So n is 4. I have 4 turtles, but we're not going to divide by 4. We're always going to divide by 1 less. So let's divide by 3. 10 divided by 3 is... And now the rounding rule is only for the end. I'm not going to round in the middle of the computation. I keep all these digits. And step 6, looking at our formula, after we divide, we just need to take the square root. And so on my computer, I'll take the square root of 3.333333333. And I got 1.8257. But we'll round that to 1 decimal place by the rounding rule. Okay. For the set A, our standard deviation is 1.8. Let's look back at the set. What that means is if I draw these green lines here, 1.8 below the mean is at 1.2, and here, 1.8 above the mean is 4.8. Looking at those 2 spots, if I try to spin this bar on my finger, then it's going to spin as if all of the mass was sitting at those 2 green lines. And so those give us the measure of spread. Wow, that was a lot of steps, wasn't it? So now you've seen one example of standard deviation. Let's do the math for B and see whether B is more or less spread out than A. I think we can predict B is probably more spread out than A, right? So now I'm going to stop sharing and we're going to go over to Excel for a while. So hopefully you can see it this time, but if not, we are taking a recording. This thing is very slow. Stop presenting. You know, Apple, okay. So now if I share my entire screen over here, can you all see that? Okay. This time I can't see it on the iPad, so I'm getting whatever problem you were having before. Goodness gracious. I hope it'll be in the recording. So, here on the screen then, B had 3 points. The x values were 1, 1, 1, and 9. Hold on just one moment. Okay, so we're going to try to compute this 3 different ways with Excel. So one way is to follow the steps we just set out. Let's find out what is x bar. And I'm going to say that is the average of all of these points. So they have an average of 3. Next, I need to ask, what is the deviation for each point? So that's going to be equal to this point minus the average. And here, I'm going to press F4 to make that an absolute reference. What that means is that if I, and we'll explain this again once we're in class in person, if I go down here, I can say, Excel, I want you to fill down, and it's going to say, here is A3 minus A8. Here is A4 minus A8. Here is A5 minus A8. So it calculated the deviation for each of these, but it always used the same x bar because I made that an absolute reference. We'll go over that again once we're back together. But there's my deviations. These are each 2 inches below, and this is 6 inches above. Step 3 is to square our deviations. So I'm just going to multiply each one by itself. Control D to fill down. All right. Step 4 is to add all of our deviations squared. So I'm going to ask, what is the sum of these numbers? They add up to 48. We want to divide 48 by 1 less than the number of elements. There's 4 elements, so we divide by 3 to get 16. And then the last step, we take the square root. So the square root of 16 is 4. So this set has a standard deviation of 4. If all of the masses were 4 inches away from the center, instead of 3 of them being 2 inches and 1 being 6 inches, if they were all 4 inches, it would be balanced the same. So B was a little bit more than twice as spread out as A. So there's standard deviation in Excel. So that's the slow way. Now let me show you the very fast way. I say equals stdev.s, and that's the name of the command, stdev.s. I highlight my data set, and it says the standard deviation is 4. Okay. And now, since I made this all with dynamic references, if I change the set, we can see that this works for the other set. So the other set was 1, 2, 4, 5. We can see that they have a standard deviation of 1.825. So anybody with any set with 4 elements, we could do the standard deviation in this same spreadsheet. Never have to do the same work twice in Excel. It's very handy. Okay. So that's how to calculate a standard deviation. There's the slow way and the fast way. Now, why would I ever bother teaching you the slow way? Well, the fast way only works if you have a list of all your data points. So, if I have my cat problem, if I want to know the standard deviation, the mean was easy, right? Let's start by getting the mean. We're going to do x times f. So frequency, multiply by the number of cats. 5 people have 1 cat, that's 5 cats. 10 have 2 cats, that's 20 cats. 10 have 3 cats, that's 30 cats. Then we'll take the sum of all the frequencies. The sum of all the frequencies is 40. There's 40 people in my study. The sum of all of my XFs is 55. There's 55 cats in the study. Excuse me. So then my X bar is equal to 55 divided by 40. There are 1.4 cats per household in this study. So that's how we get the mean from a frequency table. But now I want the standard deviation. So for each of my 4 responses, I need to go through my 6-step formula. Step 1 was find X bar, which we did. Step 2, I'm going to add a column for deviation. How far is this guy from the mean? That's going to be equal to this minus that. And I hit F4 to make it an absolute reference. So you have 1.4 cats less than average. If you have 1 cat, you have 0.4 cats less than average. 2 cats is 0.6 more than the average, and 3 cats is 1.6 more than the average. So here's our deviations for each house. Step 3, deviation squared. So I take this number and square it, fill down. It seems that the square of 0.4 is 0.14. 0.14 square cats. What's a square cat? I don't know. But we have to find this as part of the formula. Now we add up all of our deviations squared. Step 4 is to add all your deviations squared. That adds up to 5.06. Step 6 is to divide by n minus 1. Now, are you thinking divide by 3? Because that's not what we want. There are 40 people in this study, so we're going to divide the sum by parentheses 1 less than 40. We'll divide by 39. Altogether, oops, I've made a mistake. I'm sorry. 1 person with 0 cats has a deviation squared of 1.89. 1 person with 1 cat has a deviation squared of 0.14. The 2 cat people have 0.4 and the 3 cat people have 2.64. That's the deviation squared for 1 household with 3 cats. Each household with 3 cats contributes 2.64. I need to do my deviation squared multiplied by my frequency. If 15 people each have a deviation squared of 1.89, 1.89 times 15 is 28. Together, these 15 people have 28 deviation squared among them. Now we can fill down. My 10 3-cat houses have 26.4 squared deviation among them. So these are the sums of the 40 deviation squareds for the 40 households. 15 of these, 5 of these, 10 of these, and 10 of those. So that's a step I almost forgot. It's hard when all of your notes are in Noonan and you're giving a lecture from Carrollton, I'll say that. But I think I've remembered most of it. So we have all of our deviations squared. Now we're going to add those together. So these 40 households all together have a deviation squared of 59.3. There are 40 houses, so we're going to do 59.3 divided by 1 less than 40. 40 minus 1 is 39. When you have 59 depths squared for 40 houses, if you divide that equally 39 ways, each person gets a depth squared of 1.5, and then the last step is the square root. Okay, this study had a standard deviation of 1.2 cats. Goodness, what a process that was. I'd like to show you one other way to get the same answer. It's not as high tech. It's not going to be customizable later. But if I just type in 0 15 times, let me highlight those and make sure that's 15. Oop, that's 14. I need one more 0. There's 15 zeros. Here's 5 ones. That's too many. There's 10 twos, and here's 10 threes. This is the low-tech way to get the same answer. I manually typed 15 zeros, 5 ones, 10 twos, and 10 threes. So now, if I take the standard deviation, I can just say stdev.s, and it should give me the same answer as what I got above. Assuming I did all of this correctly, there's the same number. So there's 2 ways you can get the standard deviation from a frequency distribution table. You can see it's not pretty, but I will put this Excel spreadsheet on your course den so that you can reference this as you're doing your homework. Okay. We have 1 minute left. So I guess I'll tell you about that one other thing on Monday. We've gotten through most of it. All right, you should be able to do everything except for the very last problem in 1.3. And then when we get back on Monday, we'll do section 1.2 together. Thank you all for joining me today. I'm going to put this spreadsheet on your course den, and then I hope you have a great weekend. I'll stick around for a minute, so type in chat if you have any questions about anything. Otherwise, stay warm, stay safe, and I will see you next week. Yes, you too. Have a good weekend. Thank you. Thank you. Bye. Okay. Well, that wasn't so bad.